Okay, so welcome back. As we were discussing the boundary work, we will continue with a little more analysis. Now we will consider a process which is commonly used for this expansion and contraction in the piston gas cylinder. So this is a process called polytropic process. In such case, your P and V have a relation with such that P V to the power n is constant. So this is a common actual process, expansion and compression. This relation is called polytropic process. So let us consider such a process in a quasi-static equilibrium conditions, and our interest is to find out the boundary work for such a system when the gas expands and contrasts having this relation of P and V. So we will consider again WB boundary work, and we will make use of this expression. Okay. Again, this is true the P when assuming it to be quasi-static equilibrium, so that make use of the pressure of the gas in the system. So we can put P as Cv minus n dV. This can be written as C V2 minus n plus 1, V1 minus n plus 1, and this is minus n plus 1, or we can write this as, because C is constant here, and we can take out V2 to the power minus n, together it becomes P2, and then the remaining V2 will be here. Similarly, we can write P1 V1 and minus n plus 1. So we can simplify this in this form. Okay. Now if you are considering an ideal gas, then we can make use of the ideal gas equation of state and replace PV by MRT in terms of temperature. So you can write for ideal gas PV is equal to MRT. So thus your WB is MR T2 minus T1 1 minus n. So note that n should not be equal to same. So this is the true for n not equal to 1. Okay, so this is the typical PV diagram process path for such a system. Of course, it depends on the value of n, and we are going to discuss this the effect of n on the work by considering different values of n. I will illustrate in an example. Okay, so let us consider starting with n equal to 1. Now if you consider n equal to 1, you have a system PV is equal to C. Okay. Now if for an ideal gas n equal to 1 turns out to be an isothermal process, because for an ideal gas PV is equal to MRT, when you say this to be C constant, which essentially means temperature is constant, and in that case you can come up with an expression. So you can replace P in the boundary work expression by Cv to the power minus 1, and this will lead to this expression for the case of n equal to 1. And similarly, you can also find out the boundary work for a constant pressure process, and this would be your simply P0 V2 minus V1. And what about the boundary work for a constant volume process? Now considering the boundary work where dV is not changing, it should be 0. Okay, so let us try this polytropic process with different values of n and understand by an example. So consider this is a system. So this is a system of gas in a cylinder. Okay, this is a piston. Okay, piston contains small weights which are represented here. These are the weights, and initial pressure is 200 kilopascal, and initial volume of this system is 0.04 meter cube. Now, so there are many different parts we are going to do that. The first part is where we are going to heat up the system using a Bunsen burner, so placed under the cylinder here. Okay, so we are going to provide Q in and let the volume of the gas increases. So we want to increase to 0.1 meter cube while the pressure remains constant, keeping the pressure constant because the weight is constant. So the P0 external and other aspects are constant. So hence your pressure is constant, only the volume is going to change. So what we have to do is we have to find out the work done by the system on the surrounding. So we are going to simply put WB as simply PdV. Now in this particular case the pressure is constant, so this is going to be simply P V2 minus V1, and pressure we know is 200 kilopascal. Final volume is we know minus 1, and the initial volume is 0.04 meter cube. This is going to be 12.0 kilojoules. So that was the first part of this example. Now let's consider the same system and the same initial conditions. So you have 200 kilopascal, you have 0.04 meter cube as initial volume, but at the same time when we place the Bunsen burner under the cylinder and the piston is rising, what we are doing is we are removing the weights. So while we are providing the heat, we are also removing the weight in such a way that the temperature is constant. So we are keeping the temperature constant. So now the question is what would be the work for such a system. So again we are going to make use of the ideal gas here. For the gas we are going to make use of ideal gas equation of state. So PV is equal to mRT. Okay, now temperature is constant, which means this is C. So WB is PdV, and we have already calculated or derived the expression for the constant temperature expansion. So isothermal process and that would be P1 V1 ln V2 by V1. So this we can obtain the values by putting the values for each variables. Now P1 is 200 kilopascal, V1 initial volume is 0.04 meter cube, and then ln 0.1.04. Okay, so this turns out to be 7.33 kilojoules. Note this is less than the previous one, which was constant pressure work. Okay, so this is a constant temperature work, and the previous one was a constant pressure work, and the final state in terms of volume is same. So now let's consider the third case. Now in this case you have the same system, but now during the heat transfer we remove the weight at such a rate that this expression is constant. So this is a polytropic process which describes the relation between pressure and volume during the process. The final volume is still the same, which is 0.1 meter cube. So we are going to calculate the work for such a system. We make use of direct expression of the polytropic process. So this means that we have P1 V1 is same as P2 V2 is constant. Okay, or we can write P2 is P1 V1 by V2 1.3, and WB we have already calculated the expression. This was P2 V2 minus P1 V1 1 minus n. N here is 1.3, and you know P1, which was 200 kilopascal. Okay, you know initially this is your 0.04 meter cube. P2 you can calculate from this expression. So this turns out to be 60.77 kilopascal, and then you plug in these values in this expression. So this comes out to be 60.77 into 0.1 minus 200 into 0.04, 1 minus 1.3 kilopascal meter cube. The answer is 6.41 kilojoules. So this is the work done during this process having a relation between pressure and volume in this form, polytropic process. Okay, so let's take a last case for this example. So in this case you have the same system, same initial condition, but let the piston be held by a pin, which essentially means that the volume will remain constant in this process. Now so volume remains constant. In addition, let heat be transferred from the system until the pressure drop to 100 kilopascal. So you have a system now which you do not allow the volume to move, but you allow heat to transfer from the system to surrounding. So what will be the work? Work is dependent on the volume. The boundary work, particularly in this case, depends on the volume change, as we know from the expression. Now what is the volume change? Volume change is 0, and thus this is going to be 0. So let us summarize all the 4 parts of this example in a graph. So this is the pressure volume, and this represent different processes which we have considered. This is the constant pressure process. Okay, this was the case where we considered isothermal. This was the case which we considered 1.3 polytropic, and this is the case where the volume was constant. So this is where n is 0. If you look at PVN constant process, then this was the case where n was 0, and this was the case where n approaches to infinity. Okay, and this is where n is equal to 1. Okay, so you can clearly see how the work varies depending on the variable n here for the polytropic process. Okay, so with that we are going to end this lecture. Okay, in the next lecture we will take up the generalized energy balance, which is applied to the closed system with few examples. So see you in the next lecture.